have seen the first part of the power system, which is the generation station. So next, we want to look at the second part of our power system, which is the transmission system. Like we said earlier, the electrical energy that is generated at the generation station, we need to move them or evacuate them to where it will be used. So the first section after the generation station that the generated voltage will come to is the transmission system or transmission line, okay? So as you can see on your screen, remember our generation station is generating at about 11 kV. So we will need to move that to where it will be used. I would say we need a transmission line. And then if you look, you see that we have a step-up transformer. If you are not too familiar with these circuit symbols, you should check out our training on electrical diagrams, where the various symbols that are used to represent electrical components and equipment, they are clearly explained, okay? So at the generation station, it generates at 11 kV, and then we have a transformer close to the generation station. Like we said earlier, is the beginning of the transmission system, and that will now take the voltage from 11 kV to about 330 kilovolts, which is the transmission voltage. So later in the course of this section, we will see the reason why we need to transmit at that very high voltage, okay? So as it is moving closer to where it will be used, it is stepped down from 330 to 132 kV, okay, in the secondary transmission system, okay? So as you can see on your screen, this area is the primary transmission system. Then we have the secondary transmission system also. Now, the 132 kV is further stepped down at another substation from that 132 to 33 kilovolts, okay? So that is the end of the secondary transmission section. So the 33 kV is sent to an injection substation, where it is further stepped down from 33 to 11 kV, as we explained earlier in our introduction to power system, the first part of the first session of this particular training on electrical power systems. So when you look, the injection station has a transformer that takes it from 33 to 11 kV, and then that is the beginning of our distribution system. And then we have closer to our load transformers that will take it from that 11 kV to 415 volts or 415 volts, which will later be fed to consumers. So all of this, okay, from the 33 kV line to 415, they make up the distribution system, okay? So now, if you look at it clearly, this is the transmission system. So you see that the first component or equipment that you will see in the transmission line, okay, starting from here, is what? The step-up transformer or the transmission transformer. So as clearly shown by the voltage transformation ratio, it is meant to take the voltage from a lower level to a higher level. That is why it is called a step-up transformer. In this case, it is taking it to 330 kilovolts. That is the voltage that we transmit in this particular region or this particular part of the world, okay? So this is an example of the transmission transformer. So here we have the power plant, and then the output from the generator is fed to the transformer, and then the transformer output, okay, they are connected straight to the transmission lines. So next to the transmission transformer is the switchyard. Remember, we said we must have a means of switching it, okay, from the generation station to the transformer, and also from the transformer to the transmission lines. That helps to switch the level kV. They are within the plant. Then after the generation station, then we'll be looking at very high voltage, 330 kV. Okay, so we have, in most cases, those switch jars placed outside, okay? They are outdoor switch jars. So those switch jars, they make up what? The switch yard. The yard where the switching is done from the transmission transformer to the transmission lines, okay? So as you can see, this is an example of a switch yard. You can see the circuit breakers. This is the transmission transformer, okay? You see that the transmission transformer, the output, the input, as we all know, is from the generator. The output goes to these circuit breakers that are connected to your transmission lines, okay? As you can see, they are connected to your transmission lines. So this is the transmission line. This is the switch yard, okay? Because we have these outdoor breakers that is meant for switching. So these are the transmission transformers. Then these are the transmission lines that takes the 330 kV, okay, from this particular switch yard to the transmission lines. So these are what we'll see basically in the transmission system. So in the transmission system, we'll see, as we have it earlier, we'll see the first, the transmission transformer, which is a step-up transformer that will take it from 11 kV that is generated at the generation station to 330 kV. Then we have the switch yard in the transmission system immediately after the transmission transformers. So that switch yard there is where we have those circuit breakers and all other protective devices, okay, that are meant for switching the power onto the transmission lines. And then we have the transmission line. And then at the other end of the transmission line, we will have a step-down transformer that will take it from 330 kilovolts to 132 kV, okay? We also have switch jars, the ones that will receive the 330 kV before it goes to the transformer, and then after the transformer, the one that will deliver it into the 132 kV transmission lines, okay? So we have switch jars at the first substation, okay, in the transmission system, which is the switch yard. Then we have another substation at they call it the 132 kV substation. Then at the other end of the 132 kV, we also have the switch jars that will receive the 132 kV before it takes it to the another step down transformer that will take it from that 132 kV to that 33 kV, okay? So that is where the transmission lines actually terminate. We also have another set of switch jars that will receive this 33 kV and send into the 33 kV lines, okay? So here you see this is a complete power system showing the power plant then the switch yard containing the transmission transformer or the step-up transformer that will take it in our case to 330 kV. This is the transmission line to the sub-transmission system, okay? Then further down, it is stepped down until we get to the distribution levels, okay? And to our ultimate consumer. So you will see that at every point of changing the voltage from one level to another, we have substations, okay? And the primary equipment or principal equipment in that substations, they are the transformers and the switch gears, okay? Now, back to what we said earlier, you can see that the voltage that is generated maybe at 11 kV, we cannot send that 11 kV, say, down to this particular substation, okay, where it is stepped down from 33 kV to that 11 kV. So now, why do we need to have this voltage stepped up? You'll see that the transmission system, as you can see, it is designed basically to reduce voltage drop. That is two things, voltage drop and power losses. Now, let's take them one after the other. Voltage drop. You know that voltage drop from Ohm's law, which is V is equal to the current times the resistance on the line. And as you well know, all the power that is in the power system, okay, from that is generated at the generation station is taken to your load through those conductors. Are we getting it? Copper conductors. So these copper conductors, they all have some level of resistances. Okay, so once the power is on, that is there is load on the line, you will see that some level of current will be flowing on the line. Okay, and that current, as it is flowing through the line, definitely, since we have some resistances on the line, it will cause some voltage drop from that Ohm's law. V is equal to IR. So eventually, you will see that the voltage that we have at the end, where we want to use the particular voltage signal, may not be up to what we actually expected. Assuming, okay, let's say here now we need 11 kV, we are generating 11 kV here, okay? So assuming we are transmitting over a distance of some kilometers. So once the load starts coming into this particular system, you see that as the current is flowing, okay, back to the source of the power, you see that there will be some level of drops, okay, along all of these copper conductors or these copper wires that have some levels of resistance. It therefore means that if 11 kV is generated here, we will not have that exact amount of 11 kV here, okay, because there are some drops along the line. So that would mean that the more load we have on the network, the more drop we'll have on the system. And that is not a desirable condition, okay? We want to minimize the drop as much as possible. We want to have the required amount of voltage at the end where we actually require that. So if you look at these transformers, so you notice that, you know that their transformation ratio, they are fixed. So if your input is low, definitely the output from it will be low, okay? Which means if we are expecting 415 in our output, we may not have up to that 415 face-to-face. We'll be having, say, 300, which means a face and neutral will be less than 180. Will be less than 180 fed to our load. Okay? So all of these, they are not desirable conditions like we said earlier. So we need to minimize that voltage drop as much as possible. Okay, so how do we minimize that voltage drop so that we will not have reduced voltage at the other end of the power system? It is very simple. There we have the formula V is equal to I R. Okay, so if we can reduce the I, okay, we can reduce this I, what will then happen to the drop? The drop will drastically reduce. Are we getting it? So there are several ways we can do the reduction of this, but principally, okay, we want to reduce this by increasing the voltage supply, okay? That is increasing the transmission voltage, I mean to say. You know, the power in the system is constant because the power in the system cannot be more than the power at the power plant, okay? I will know that power is a product of the voltage and the load, that is the current on the system. So since this is constant, we can only play with V or I, okay? So since this is constant, if V is going up, I will do what? Will come down. If I is going up, V will come down, okay? Because both of them, they are inversely proportional from that particular power equation. So now, we need small I because we want to reduce the voltage drop. Are you getting me? So for us to reduce this I, it means that we need to increase this, okay, so that this will be as small as possible, okay? So if we have this to be as small as possible, it means that the drop along the transmission and distribution line will be small, okay? So that is what actually informs the transmission of this voltage signal of power at very high voltage. In addition to that advantage, you will see that it also helps to reduce the power loss. Like we said earlier, all of these cables, they are made of copper wire, which have some level of resistance. I will know that power loss from this formula is a product of the square of the load or the current on the line and the resistance of the line. So if we are able to reduce this, since this is constant on the line, okay, though it is dependent on the temperature of the lines, okay, but since this is relatively constant, if we can reduce I, it means that we will be able to reduce this power loss drastically because it is the square, it is a product of the square of the current and the resistance. So if we reduce this by increasing V, okay, that means we also reduce the power losses. So another way that we can reduce the power loss is by reducing arrow. Okay, is by reducing arrow. So another way we can reduce power loss is by reducing arrow. And to reduce arrow, it means that we need to increase the cable size. Okay, so increasing the cable size will invariably reduce arrow because from the formula, arrow is equal to rho L over A. Since we are increasing the cross-sectional area A, you see that arrow, okay, since it's inversely proportional to A, will reduce when we increase A. That is the size of the cable. But there is a limit to which we can actually increase the size of the cable, or else the cable will become too heavy and more expensive for us to use. Okay, so the best option is for us to increase V with the use of our transmission transformers. Okay, and then reduce that V when we get to where we actually want to use the voltage. So that is the second way, but those are the two ways that we can actually reduce the power loss and the voltage drop. Okay, so this is the basic reason why we need the transmission lines, why we need to step up the voltage to that higher level, okay, for the transmission lines. It is basically to reduce the voltage drop and also to reduce power losses, okay? So if we are able to achieve this, it means that the efficiency of the power system will be increased. And that is one of our goals in operating our system efficiently.